Hello, my name is Osvaldo Ochoa. I'm a technology student at the Universidad Autónoma del Estado de Hidalgo, and this is a project focused on the design and synthesis of a nanosystem of zinc oxide quantum dots, functionalized with theophylline to evaluate their hepatoprotective effect. But why is this important? Why is it essential to develop new research in nanomedicine? It is crucial because liver disease ranks among the top 5 causes of death globally. Additionally, finding truly effective treatment to control liver damage is very challenging. This is where the use of nanoparticles becomes one of the most promising areas in the field of medicine due to their versatility properties including viability, therapeutic potential, and diagnosis capabilities. But why focus especially on zinc oxide nanoparticles or zinc oxide quantum dots? This is because in recent years they have become frequently subject of study due to their good biocompatibility, low production costs, antibacterial and therapeutic properties. Moreover, in treatment for diseases such as diabetes, heart problems, and liver issues, they have shown good performance, and specifically in liver disease. They can slow down or control damage by reducing lipid peroxidation, oxidative stress, and thus hepatic fibrosis. On the other hand, the family of methylaxanthines has not only demonstrated beneficial effects in the treatment of asthma and other respiration conditions, but also in some studies related to liver disease. Theophylline, though less studied, is a member of this family and has shown promising results in treatments related to liver damage, thanks to its antioxidant and anti-inflammatory properties, which can reduce fat accumulation in the liver as well as the level of certain cytokines. Despite the properties of both compounds, the biological activity of theophylline and zinc oxide has only been evaluated separately. This is where the idea arises. Why not create a synergetic effect between both? By doing so, we could explore the potential benefits of this interaction that might otherwise be overlooked. To accomplish the development of this project, it was divided into stages. The first one, DFT molecular simulation analysis. The second one, synthesis of the nanosystem using the chemical precipitation method. Number 3, characterization of the nanosystem. And number 4, an in vivo evaluation of the hepatoprotective effect. Within the methodologies, I will begin by explaining molecular simulation, as this theoretical analysis provides a solid foundation for understanding the feasibility of chemical functionalization. If the simulation shows favorable interaction, it is likely that these bonds will also form in a real experiment. On the other hand, if the interactions are not favorable, it may be necessary to reconsider the functionalization approach or explore other chemical conditions. This theoretical analysis leads to more suitable chemistry, avoiding the high cost of necessary resources, saving time, and reducing environmental pollution by minimizing chemical waste. To develop the nanosystem, as we can see in Figure 1, it was necessary to use a coupling agent like citric acid to improve the bonding between the nanoparticle surface and theophylline. This need arises due to the possibility lack of activity or affinity sites on the surface of zinc oxide quantum dots to interact directly with theophylline. Here, first the geometries of zinc oxide, citric acid, and theophylline were separately optimized using density functional theory with LSDA functional and the 631 plus GDP basis set via Gaussian O9 program. This was done to later determine the binding energies between the complex zinc oxide citric acid and citric acid theophylline molecules using the V3 functional and the D0UVP2 basis set. In the experimental methodology, the synthesis of zinc oxide quantum dots began with the use of the chemical precipitation method due to its lower cost compared to other methods like CVD, its lower temperatures, and scalability. 2 ethanolic solutions were prepared, referred as solution 1 to a zinc acetate solution acting as a precursor of donor of zinc 2 plus ions, and a solution 2 to a lithium hydroxide as a reducing agent to perform the zinc oxide molecule. The parameters controlled during the process include pH, temperature, time, and agitation. For the functionalization process, a solution of citric acid was prepared and added to the zinc oxide solution with the intention of covering the zinc oxide quantum dots. Once agitation was complete, the sample was centrifugated and the sediment was dried in an oven, after which the obtained powder was collected. To add theophylline to the system, an equimolar solid-solid interaction was carried out between the zinc oxide and citric acid complex, powder, and theophylline using a mortar and pestle, applying force for a certain time in a humid environment. For the in vivo methodology, normal weight Winstar rats were used. Their behavior and viral signs were monitored for 2 days. During this period, they were administered with zinc oxide, theophylline, and the Nanosystem, as shown in Figure 3. 9 groups of 6 rats, each one, were formed, and after 38 hours, each group was sacrificed by exsanguination through cardiac puncture under anesthesia for subsequently determination of biochemical parameters such as alkaline phosphatase, gamma-glutamyl transpeptidase, alaninoaminotransferase, and bilirubins in plasma, as well as lipid peroxidation, proteins, glycogen, and catalase in liver. Moving to the results, in the molecular simulation, we found that the energy results of the system indicate the interaction between zinc oxide citric acid and citric acid theophylline is negative and significant, suggesting that the bond is energetically favorable. The high electronegativity suggests that the zinc oxide citric acid interactions tend to polarize the bonds, facilitating a stronger interaction with other molecules, such as theophylline. The magnetic dipole moment indicates a strong charge separation without our system, leading to high polarization, which favors the orientation and specific bonding of theophylline with the zinc oxide citric acid complex, making the interaction more stable. This led us to propose 2 possible interactions. The first one, indicating a possible electrostatic interactions. The second one, suggesting the formation of ester bonds and or hydrogen bonds as shown in Figure 6. For the experimental results, characterization techniques were necessary. First, we need to ensure the successful synthesis of zinc oxide quantum dots. After completing the solution, it was exposed to UV light to observe its photoluminescence. In the case of quantum dots, the middle wavelength is associated with the observed color. Emissions in blue and green were obtained, as shown in Figure 12, indicating wavelengths of around 3 to 5 nanometers and 5 to 7 nanometers respectively. This suggests very small particle size. Additionally, an UV spectroscopy analysis was performed, showing Figure 7, which demonstrates the characteristic absorption band of zinc oxide between 300 and 320 nanometers, indicating the correct synthesis of zinc oxide nanoparticles. To demonstrate the formation of the nanosystem, an FTIR study was conducted. The pink spectrum corresponds to zinc oxide nanoparticles, the red to citric acid, blue to theophylline, yellow to zinc oxide citric acid interaction, and green to the nanosystem. In the yellow zinc oxide citric acid spectrum, we observe an attenuation in the band of the hydroxide groups compared to the pink zinc oxide band. This result was expected due to the covering of the citric acid, but we can also see the zinc oxide bond is still present around 500 and 600 wavelength. In the green nanosystem spectrum, we observe an attenuation of the carbon and the hydroxyl groups within 1000 and 105 range compared to the red citric acid spectrum, and an increase in the carbonyl groups at 1560 and 1721 wavelengths compared to the yellow spectrum, while the theophylline fingerprint continues to appear as seen in its blue spectrum. This indicates the correct anchoring of theophylline. The size distribution of the nanosystem was determined using DLS analysis, shown in Figure 8. There are a normal distribution in observed, with an average particle diameter of 375 nanometers. Additionally, as we can see in Figure number 10, morphology analysis was performed on zinc oxide and the nanosystem using a SEM at 3700 and 10,000 magnification respectively. The correct formation of the nanosystem was furthermore confirmed using EDS, where the percentage of weight of the element of the nanosystem is displayed, confirming the absence of the impurities. Once these tests were completed, and adhering to the normal official standard norm 062-000-1999 for the production, care, and the use of laboratory animals, we proceed to analyze the effects of the nanosystem on rats. We observe that the groups treated with the nanosystem at concentration of 100 mg per kg and 50 mg per kg, represented by the last and second two last bars respectively, generate the following effects compared to the groups damaged with tetrachloride. Prevention in cholestasis, evidenced by the reduction in alkaline phosphate and gamma-glutamyl transpeptidase levels. Decrease in necrosis, indicated by low alaninoaminotranseptidase levels. Maintenance of the liver functionality, determined by total bilirubin levels. The protection against oxidative stress, demonstrated by the reduction of the free radicals determined by lipid peroxidation, catalase, and glycogen. With this, we can conclude that, first, the DFT study shows that the main forces that enable the formation of the nanosystem are electrostatic interactions, hydrogen bonds, and ester bonds, in addition to contributing to the more sustainable chemistry. Second, is that the synthesis of the zinc oxide using the chemical precipitation method proves to be efficient to the formation of nanoparticles. The third one is that the characterizations, such as FTIR performed on the nanosystem, confirm that the coupling agent citric acid can effectively coat the zinc oxide nanoparticles and allow anchoring the theophylline. Another one is that the administration of the zinc oxide theophylline nanosystem in biomodels demonstrate hepatoprotective effects, reducing cholestasis and oxidative stress, while maintaining liver functionality as well as glycogen content. But before we suggest the nanosystem as a potential next generation treatment, we recommend to conduct studies such as TGA to determine its stability and continue with in vivo studies to evaluate its long-term effectiveness and safety. Thanks for your attention.